I'm recording now. So this is our multiple input, multiple output system. We've got. Can you put yourself on mute if you're not on mute? Because I can hear someone chatting away.
Then after at night, I cook the meatball and pork. You can eat my pork tonight, so the meat pork.
Muted everyone. Okay, so multiple input, multiple output. Transfer functions G11, G22, obviously linked M1 to Y1, M2 to Y2, but we've got G21 and G12 as well. And those interactions are going to cause coupling between different inputs and different outputs. And we need to work out which are the most sensible connections to make if we're making control loops. And we've limited ourselves to single connections from one output back to one input. We're not attempting multivariate control where you're taking multiple outputs into a single controller and doing clever things with them there. But we have a choice, so Y1 could go to M2, Y2 could go to M1, or Y1 could go to M1 and Y2 to M4. And obviously as the number of inputs and outputs increases, the number of possible combinations of connections increases rapidly. So we want a method to decide, is there a way of doing that which is reasonable? And if not, then how we do decoupling. So in the session today, I'm not going to look at decoupling, I'm just going to look at two examples where we're looking at this system and understanding the methods we've got for tackling it. Okay, so the two problems I'm going to go through are similar to the ones that are set for the tutorial, but with different examples. And by talking through those, you'll get an idea of how we're dealing with these. Okay, so the first one is we want to be able to start with the equations that describe a system and turn that into our description. So first of all, we're going to start with some differential equations. So that's one of them, and this is the second one. Okay, so we've got two differential equations. What sort are they? They're linear, and they're ordinary, and they're first order. And so we want to do our control analysis to this. So the first thing we need to do is take the Laplace transforms, and we're given a bit more information about their initial conditions, which will be helpful to us for doing the Laplace transform. So we'll do the Laplace transforms, and then we have 2y1 plus y2 plus, so there should be 2s, y2 times s, y1 plus y2 equals m1 plus m2. And I'm saving myself a bit of time by not writing the bars over the top or the s's in, but now all of these are Laplace transforms. So now we're looking at the Laplace transforms. And the second equation goes to s times y1 minus 5s y2 plus 2y1 minus y2 equals m1 minus 2m1 m2. Okay, so we've got those, and now we want to turn them into the matrix form. So you can see you've got some y1s here, you've got some y2s, so we need to group those together, and then we can write it out as our matrix equation. So we've got 2s plus 1 times y1 plus s plus 1 y2, that's equal to m1 plus m2. And then here we've got s plus 2 times y1, and now we've got minus 5 minus 1 y2 equals M1 minus 2 M2. So having done that, we can write this out as our matrix equation. So in our matrix, we're going to have 2s plus 1, s plus 1, s plus 2, minus 5, minus 1, minus 5s, minus 5s, minus 1. Equals times y1, y2. And then we've got our m's. So it's going to be 1, 1, 1 minus 2. Multiplied by m1, m2. So that's going to give us the same equations as these. And now they're written as matrix, we can rearrange that conveniently to get our expressions for y1, y2. So we need to multiply by the inverse of this matrix, and that will give us an expression for y1, y2. So the inverse of the matrix is 1 divided by the determinant, which is 2s plus 1 multiplied by minus 5s minus 1 minus s plus 2 times s plus 1. So that's 1 divided by the determinant. And then we swap these two terms and make those two terms negative. Like that. And then that's multiplied by this one, 1, 1, 1 minus 2, m1, m2. So how's that looking? It's looking okay. It's looking a bit laborious algebraically, but everything's fine. So now we need to get a single matrix out of these two, and we need to sort out this factor here so we can see what that looks like. So first of all, doing the factor, we need to group up this to get our polynomial. So we have minus 10s minus s, so that's minus 11, sorry, minus 10s squared minus 1s squared, so it's minus 11s squared. We got minus 5s minus 2s and minus 3s, so that's minus 10s. We've got minus 1 and we've got minus 2, so that's minus 3. So that's our polynomial there. And then here we need to multiply these three. So it's minus 5s minus 1 plus 2s plus 1. So that's going to be minus 3s. Sorry, that's not. That's going to be minus 5s minus s, that's minus 6s minus 2. And then we have this one, minus 5s minus 1 multiplied by minus 2 times minus s minus 1. And you work that out, it's minus 3s plus 1, and so on. You get s minus 1 minus 9s minus 4. Okay, so we can take our second order simultaneous differential equations, and by using the class transform and by doing the matrix rearrangement, we can get ourselves equation for y1, y2 as this linear equation for in terms of m1 and m2 and our functions of s. So we're interested in this system, and what its properties are going to be and how we should tackle it. So our concerns are about what control loops we should use, and our concerns are about is it stable or not. So if we're assessing stability for a system like this, we need to look at the characteristic equation and look at what the roots of that are, and we want the real parts of the roots to be on the left-hand side of the real imaginary plot. So we want to have negative real parts to all of the roots of our characteristic equation. And the characteristic equation depends on how you arrange your control loops and so on. So I've written some of this out in advance to make it a bit easier. So here's our setup, and we've added in some control loops. They go from Y2 to M2 and Y1 to M1 as we've written it. Obviously it's arbitrary, because if you wanted to, you could swap your M's in terms of what they are. So this is just a generic formulation. You can see our network of transfer functions within the block. And this is obviously just for a 2x2 system, but we want to check that we can have the method to find the characteristic equation for a system like this. Okay, so how are we going to do that? Well, we can write out the relationships. So Y1 is equal to G11. So Y11 is equal to G11 times M1 plus G12 times M2. So those two things come together to make Y1, and likewise Y2 is equal to G22 times M2 plus G21 times M1. So we've got those two equations, and then we can also look at this point, and M1 is equal to Y1 SP minus Y1, and M2 is equal to K2 times Y2 SP minus Y2. Okay, so we've got four simultaneous equations, which don't look too complicated at that point, but when we start to work through them, it gets a bit laborious. So again, I've worked through this in advance. So we substitute in our expressions. So we don't have M1 and M2 in it, so we need to substitute in for M1. So we can put this expression in for M1, and we can put this expression in for M2, and then multiply them through. And we get this one to begin with. So Y1 is equal to this expression. It's got these four parts, which are in terms of Y1 SP, Y1, Y2 SP, and Y2. And likewise, you do the same for Y2. So now we've got two simultaneous equations. We've got rid of M1 and M2. We've got two simultaneous equations, Y1 in terms of Y1 and Y2. So again, we want to solve these so that we just have an expression for Y1 in terms of Y1 SP and Y2 SP, and likewise for Y2. So we need to rearrange Y2. So this expression gets rearranged to this, and then we can substitute this Y2 into here in our expression for Y1, and then we're going to have an expression for Y1, which is just in terms of Y1 SP and Y2 SP. And so we do that like so. And so we substituted in our Y2 into here, and now we've got an expression for Y1. Let's check what it's in. Y1 SP, that's okay. Y1, that's okay. We'll just have to group them up. Y2 SP, Y2 SP, Y1 SP, Y1. So that's okay. So we've got this now in terms of y1, which we want, and y1 SP and y2 SP, which are our inputs now. So again, we need to rearrange this. We need to group up the y1s. So we can do that. So we group up the y1s on the left-hand side, and we've got all of those terms. And then we sort out the right-hand side. We've got the y1 SPs grouped up and the y2 SPs grouped up. Okay, so that's starting to use up lots of ink. Before we carry on, let's just check what we're interested in. What we want to know is, for the purposes of stability analysis, we want to know what the characteristic equation is. So what we're going to do next is divide all of the right-hand side by this coefficient on the left-hand side. And it's this polynomial here then, that's the one that's going to be our characteristic equation. And we want the roots of this polynomial to be to have negative real parts. So that's our characteristic or polynomial. QS is the denominator polynomial for the overall transfer function. That's the same as this. I've just factorized the G1, 1 plus G22 K2, 1 plus G11 K1. That's the same as these four terms here, and then minus this term. So that's the polynomial, and then to make that our characteristic equation, we make that equal to 0, like so. And we have values for all of these D12s and so on. So we've got this expression, and we previously worked out this matrix. And so these are the terms that we need to put in. So that's G11, that's G22, that's G21, and that's G12. And of course, each of these is divided by this factor, this term here. So we need to substitute those in to these terms here, and then work out what that polynomial is. So we do that. First of all, we substitute those terms in, and it's coming out like this. This is our characteristic equation. We set that equal to 0 and find the roots. So you can see this denominator here, the 11s squared plus 10s plus 3, that appears. And obviously we can start by multiplying through by that term squared, and that will get rid of that one, and then it will get rid of those two. We just have to put it in here and here. So we do that, and that works out like this. So you can see we've multiplied it through by here, and then we've got our 6K1S plus 2K1 term from that here. Same on this one, and then minus what's left here. So you can see now this is going to be a polynomial. It's going to be order 4, so we've got an s to the power 4 term, and this is what we want to find the roots of next. So I appreciate it's a bit laborious working through the algebra, but it's perfectly achievable for you. And what you want to do is to get an expression in the end where you've isolated or grouped it up for each of the s terms, like so, and then we can concentrate on finding the roots of these. And you'll have done that with Professor Costas. How do we know if that's stable? How do we know what the roots are? Well, obviously, if it's a quadratic or a cubic, we've got some methods for finding those roots. But in general, we have this criterion for stability. So if we have a polynomial a0, s to the n, a1, s to the n minus 1, and so on, you know that there's methods to find whether or not these are stable, whether they're going to have positive or negative roots. Starting point is to check each of these, A0, A1 to AN. If any of those are negative, then you know straight away that you're going to have at least one positive real part in your roots, and so therefore it would be unstable. If all of these are negative, then that's a good starting point, but it's not the end of it. It means that you might be okay, but you don't know yet. And then you need to go on to this array, which you'll have seen, where you need to then make your array out like this, find your values for A0, A1, that's the easy bit, and then you have to calculate A1, B1, C1, and so on. And again, you want all of these to be positive if you're going to have a stable system. So that's what you would do here. So obviously, first of all, we check all of the terms. So 1, 2, 1 is positive. This must be positive. So K1 and K2 are going to be positive values because we're using a proportional control. So they're going to be positive values. So that's going to be positive. 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 That's the first thing, is that they're all positive. And then you'd work through each one of this table and just calculate A1. I've not done all that for this one because it becomes even more long-winded. But what you'd see is that they are all positive in this case, and that for any values of K1 and K2, you'd have a stable system. So that was the first part of what I wanted to do, which was just to check that we're comfortable with analysing a MIMO, and that we can start from the differential equations and work through to the point where we've calculated an overall transfer function, and that we can identify the characteristic equation from that, and then identify what the roots are from a stability point of view. So that's the first thing to do in terms of how you would build or start to build a control system for them. But then we still have the question of how do you decide which outputs to connect to which inputs? What's going to be the most sensible combination of things to do there? So that's still for us to think about. So what we do in that case is this analysis that we saw in the mini lectures called the relative gain array. And it's just a sensitivity check to see how much cross interaction there is. So obviously we said before that if your G12 and G21 are 0, there's no cross coupling between the different loops, and it's a trivial case. So obviously if it's 0, that's fine. But it often won't be 0, typically won't be 0. But essentially we want to find which are the pairs that have least interaction, and then we can we can then make our control loops on the other pairs. So we're looking at these. And we're using a parameter lambda to tell us the relative sensitivity. So we can see, well, how much does Y1 change with M1? And first of all, we can do that when we set M2 to 0. So we fix that at 0, do something to M1, see how much Y1 changes. So that's fine. So that's a standard sort of gain, and that's when M2 is fixed. And it's called the relative gain because we're not just looking at the standard gain. We're looking at the relative gain of how much is this affected by M1 when that's fixed to 0, by how much is Y1 sensitive to M1 when Y2 is fixed to 0. To fix Y2 to 0, then obviously we need some control to adjust M2 appropriately. So that's that case, and that's that case. But if we have that appropriate control, then y2 can be fixed to 0. And then when we're doing that, again, we look at how does y1 change with m1 in that case. And obviously y1 won't change the same amount with m1 now because m2 is changing and y1 is a function of m2. So it's looking at how much y1 is a function of m2 by doing that. So that's our relative gain. And obviously we've calculated this for y11 here, but there are 4 possible ways of doing that. Obviously y1 to m1, y1 to m2, y2 to m1, y2 to m2. And so out of that we can make a matrix, which we call the relative gain array, which is composed of those different elements, like that. And then this is a tool for working out the most appropriate control loops to make. And obviously, if these are equal to 1, then that's great. That means there's no effect from the interaction and the cross-coupling. And so we can make our array, and then we can look for possible values where lambda is closest to 1. And a feature of this array is that if you sum the rows, they're equal to 1, and if we sum the columns, they're equal to 1. So when we're making this matrix, if it's just 2 by 2, we only need 1 value, and then we know what all of the other 3 values are. That's the basic concept of it. And we'll take a look at a question. So if we start with a system where we have y1 is equal to 3 over 2s plus 1 m1 minus 0.5 s plus 1 s plus 3 m2 plus 1 over s squared plus 3s plus 2 m3. Okay, so that's the Laplace transform of the differential equations that describes the system. And this time we notice that we have 2 outputs, y1 and y2, and we've got 3 inputs, m1, m2, and m3. And we noticed about the relative gain array that we can only do that as a square matrix. So what do we do in that case? We're going to have to look at our pairs of this and all through the different combinations of them. So we're going to have to consider pairs. You can have m1 and m2. You can have m2 and m3. You can have m3 and m1. So if you consider those pairs separately, then that will give you a complete picture of the system. So in the first case, then, we look at the pair m1 and m2 and look at the relative gain array matrix for that. So this analysis is considering the steady state relative gain. So the first thing we do for our equations for y1 and y2 is to convert them into the steady state form. And so steady state means what's happened at t infinity, and as we know that as t goes to infinity, s goes to 0. So we can rewrite our expressions for y1 and y2 and make s go to 0, so that becomes 3m1, and that's going to be minus 0.5 over 3m2. and that's going to be 1 over 2 m3. And our second equation goes to minus 10 m1 plus 2 m2 plus 4 m3. Okay, so that's the first thing. And then we want to be able to do these two differentials, dy by dm at constant m and dy by dm with constant y's. So if we look at our expression for lambda 1 first, the first part of that is straightforward, dy1 by dm1 when m2 is constant and m3 is constant as well, because we're not considering that to be an input when we're analysing these, or variable input when we're analysing these pairs. And so that's going to be equal to 3. And now to do the next one, dy1 by dm1 when y2 is constant. How do we do that? Well, if y2 is constant, that means that we can get an expression for m2 in terms of m1, y2, m3, and we can substitute that into there, or likewise into there, so that then we can do the differentiation with y2 fixed. That should be 2 there. So we can do that. So this expression tells us that m2 is equal to 10 over 2 m1 minus 4 over 2 m3 plus y2 divided by 2. And then we substitute that into our first expression. That tells us that y1 is equal to 3m1 minus 0.5 over 3 times m2. Which is the same as 1 over 6. So that's so we've substituted in to get rid of the m2, and now we can take the differential of this with respect to m1, where y2 is going to be constant and m3 is constant. And so now this differential becomes 3 minus 10 over 12, well, that's minus 5 over 6. And that's going to be 18 minus 5, which is 13 over 6. Okay, so we've got those two differentials, and that means that we can calculate lambda 1 equals 3 divided by 6 divided by 13. So that's so that's what we had. 13 divided by 6, that's going to be 18 over 13. And so then our relative gain array will be equal to 18 divided by 13 for y11. And because we know that the sums must be equal to 0, that would be minus 5 over 13 minus 5 over 13, and that would be the same. Like so. So that gives us the relative gain array for the first case where we're looking at M1 and M2. And just looking at this one, you can see a negative lambda is bad news, because that's going to make your system respond the opposite way of what you want. So that's going to be very unstable. 18 divided by 13 is greater than 1, but it's fairly close to 1. And so that would be a candidate connection for the control loop. And then you'd carry on doing that with M1, M2. You do that for M2, M3, M3, M1. And you'd look at all of the values that come out. And if you do all of them, you would get these. So the first one that we've already done was 18 over 13 minus 5 over 13 minus 5 over 13, 18 over 13. That's what we did already. Looking at M2, M3 would give us 0.4, 0.6, 0.6, 0.4. And the third one gives us 5 over 17. And from that, you would then pick the best ones for your control loops. Okay, so I will wrap it up there for this one. Thank you for your attention. And I can see there's one question to me in the chat, but that's it's been asked privately. So can I suggest, please, can you email me that question and I'll reply to it there. It's very detailed. And so now you can join your groups and talk over the problems with the teaching assistants. And thank you very much for your work on the module.